Histograms and bins. If you've been there, done that, with small samples, you know it's frustrating. The histogram is actually a tool I never recommend. Now, the histogram has a hallowed place in our history of continuous improvement. It is still called one of the seven tools of quality. I will acknowledge that the other tools are still valuable, but the histogram is problematic for a couple of reasons. One, and the worst, it is sample size dependent. Two, there are actually more efficient tools out there that can illustrate shape far more effectively. But today, we'll focus only on sample size. Hopefully, in your class, you were told you must have a sample size of at least 50. And this is very solid advice. And we're going to see today why that is the case. But sometimes you have no choice. Now, when I teach classes on statistics, at the very beginning of class, I tell all of my students, I'm going to teach you how to lie with statistics. And they all laugh, but we discuss why that's important. In order to teach you how to lie with statistics, I must teach you how to do it correctly. By teaching you how to lie, you become better consumers of statistical information you receive. You can better understand what you are perceiving, what is trustworthy, and what might not be trustworthy. Now, sometimes this is out of pure innocence, but sometimes it's out of misdirection. For today's session, I randomly generated 22 data points from a normal distribution with a mean of 15 and a standard deviation of 2. It didn't take long to find a funky data set. We'll imagine that this data was collected over time versus a single snapshot in time. Now, when you collect data over time, it is mission critical. The very first thing you do is plot that data over time. You can either do a trend chart or an SPC chart. You want to assure yourself that the mean is stationary over time. So let's go do that. So here we have an engine room, a whole bunch of different columns, and it was the ninth column that I went, this is perfect for this session. So we're going to do that. We're going to do a control chart, SPC chart, X moving range, and we have histogram data. We have this N of 22. We're going to click continue, click continue, click continue. And we can see, even though we don't have exactly 30, usually a minimum of 20 is kind of the bare minimum for an SPC chart. We see no issues with the mean not being stationary. So I feel pretty good about that. So now you learn. Let's go do some graphs. Let's do some histograms. And I would caution you, especially when you have a sample size less than 50, do not fall into that trap. Let's look at the Anderson-Darling statistic. Let's let that tell us, is this data normally distributed or not? So I'm going to do that. I'm going to go over to the N of 22. I'm going to drop that in, and immediately I get two graphs plus some statistics. So if I look over on the left-hand side with the Anderson-Darling p-value 0.5516, which would say I cannot reject that the data isn't normally distributed. So that sounds really, really complicated. An Anderson-Darling value of 0.55, very big. It says you could probably assume your data is normally distributed. You're good to go. And this QQ plot that's down here at the bottom is just like a probability plot. Statisticians kind of like QQ plots better than probability plots. We're going to talk about both in another session. But we can apply the fat pencil test to this. and all the data is going to clearly fit under a fat pencil. So we're good to go. We can assume normality. But if you look at the histogram, all of a sudden you see that looks like a bimodal distribution. You got a clump of data in those first four bins and a clump of data in the next four bins. So that doesn't look normally distributed. Why? Because we only have a sample size of 22. I used to own a data set that I could make it look skewed right, skewed left, normally distributed, and bimodal. Unfortunately, I lost that data set, but this is a good one. So this also violates another principle, actually violates two principles that I have with histograms. The first one is the number of bins should be approximately equal to the square root of the sample size. So in this case, we have 22, so we should probably only have 5 bins. In this case, we have 8, which is way too many. Now, the other problem with this is that you should always want an odd number of bins, not an even number of bins. Why? Because human beings are wired to find the center. And so when you learned about the histogram, you said it can look in the middle and figure out if it's skewed or symmetric. And in this case, the middle is in between these two bars. So all of a sudden, oh, well, the average is somewhere around 15 or so. What good guess it is. All right. So at this point, you would skip using a histogram to determine shape. But unfortunately, you got sucked into your statistics class, and the very first tool you learned about was histograms, which is the one I don't recommend. So let's do a histogram, especially when the sample size is less than 50. So we're going to put that in, and then we'll click continue, and it gives us a bunch of options, and we'll just kind of click through that. Now, good news is that on this particular histogram, where we're formally doing a histogram, we only got 5 bins. That's a good thing. All right, so that worked out well, and it kind of looks symmetric. Now, the other one looked bimodal. This one looks symmetric. So let's play some games here. Let's change the number of bins. We'll look at 8. That was the one that we had before, right? Just to refresh you. That kind of looked bimodal. Now it actually looked a little different. And one of the things that's happening is that statistical software, when you try to game the system, is going to create these weird size bins in order to create the number of bins that you want. So in this case, this first one goes from 11.94 to 12.79. That doesn't make any sense. Let's go down to 7 bins and see what happens there. I love this one. It almost looks uniform. So it's kind of symmetric, but it looks like it's uniformly distributed with that exception of one count out there. So we could get a whole bunch of different opinions about the shape of this distribution just by changing the number of bins. Now, in some software, you can also manipulate, this one looks bimodal. You can manipulate it such that you can change whether a certain number is the midpoint or it's the starting point. Again, with a sample size less than 50, you can make it look any way you want. Once the sample size gets above 50, then we're probably okay. So, why does this matter? Is your directors and vice presidents want histograms. They learned about them in college or they learned about them in their basic stats class, and they forgot this rule about sample size. They go, I want a histogram. So be careful out there. The streets are messy, and so is data. But remember, there's always a way.